Folks, exciting stuff, really exciting stuff. We're getting in to now the Helmholtz and the Gibbs. And this is exciting because in a lot of your classes, you've talked about Gibbs. You haven't talked about Helmholtz at all, but they're closely related to each other. But now we're going to see where these come from. And what we're also going to get into is our criterion for spontaneity. It's more than just delta S is greater than 0. There's a whole mess of other things that are required for spontaneous processes. And we're going to dive into that now. And we start with the Clausius Inequality, right? And I'll remind you that that is ds is greater than or equal to dq divided by t. I'm dropping all the reversible, irreversible. We're putting this together for general, for any case. Okay, this has to work, all right? And so rearranging this, we can say ds minus dq divided by t must be greater than or equal to 0. Okay? So now, we'll consider two different things. Heating at constant volume, which hopefully maybe you're thinking U, and heating at constant pressure. And hopefully from there, you're thinking H. So we're first going to start with U and H, and then we'll see the manifestations for G and A, for Gibbs and Helmholtz. Okay? So we recall heating at constant volume, so dqv gives me du, because there's no work done, so the work is 0. Okay? And so now considering this relationship right here, if I'm talking about constant volume, then that means that I can rewrite this as ds minus du divided by t, all must be greater than or equal to 0. And doing some algebra here and rearranging, I can say t ds must be greater than or equal to du. So I added that over to the other side and multiplied by t all the way through. So TDS must be greater than or equal to du. Okay, well, what if we now talk, let's think about this ds, okay? And suppose we know that that is ds. We've already imposed constant volume. So what if I said constant internal energy? Well, that means this du is going to become 0, and thus, this is what I call a criteria for spontaneity. Okay? At constant volume and constant internal energy, ds must be greater than or equal to 0. Well, we kind of already knew enthalpy had to be greater than 0 for a spontaneous change. But now what's the manifestation for U? Okay, well, what if we say now du? We're already talking about constant volume, but now what if I switch it? What if I make it constant entropy? Okay, well, that would mean that this chunk becomes 0, and 0 must be greater than or equal to du, or in other words, du at constant volume and entropy must be less than 0. Okay, and also, hopefully what you gather from this, what you see, U, natural variables become V and S from that thermo square. Beautiful. Okay, what about heating at constant pressure? Well, we know dQp equals dH, okay? And so I can rewrite the Clausius inequality as ds minus dH over t greater than or equal to 0. Okay, and so once again, we know the quantity TDS must be greater than or equal to dH. All right? And now if we impose these conditions, so for example, we know ds, we've already set at constant p, but what if we now make that constant h? Okay, well then, let's see, that's got to be greater than or equal to 0, right? Or if we said dH, still at constant p, but now what about at constant s? That's got to be less than or equal to 0. Okay, so once again, increase in entropy for a spontaneous process, but we also see that enthalpy must be negative at constant pressure and entropy for a spontaneous process, okay? And we also see the connection now of enthalpy with pressure and entropy, okay? So what about these other quantities, okay? Well, Helmholtz, by definition is the following, okay? A, 1, 2, 3, U minus TS. So it is the difference between internal energy and temperature times entropy, okay? Well, we know that basically the quantity TS really gives us heat, okay? So in other words, I can say dA equals a du minus T ds, okay? Well, recall ds is Q over T, okay? So TdS really gives us heat. So that means this definition, U minus TS, it's work. It's where we get the name, the maximum work function, okay? And so now considering our Clausius inequality, TdS must be greater than or equal to du. So now let me rewrite that. I'm looking at that and I'm like, I don't even know what it says. du, okay? So once again, the quantity T ds, right, is really giving us heat. So when we talk about the difference, U minus Q, that has to be W, right? Because we know U equals Q plus W. So this is where we get the name maximum work function out of the Helmholtz free energy, okay? So now considering that dA equals du minus TdS, and TdS has to be greater than or equal to du, okay, then what we know for this process to be spontaneous, ds has to be positive, okay, du has to be negative, and so thus, or excuse me, if I start thinking of now, let's hold temperature constant, okay? And as it turns out, I'm doing a terrible job describing this, but as it turns out, also at constant volume, this quantity has to be negative, okay? And so the reason for the constant volume is because now we're saying at constant volume, work will be equal to 0, okay? And if du has to be negative for that spontaneous process, then at a minimum, dA dt dV has to be less than or equal to 0 for a spontaneous process, okay? And then similarly for Gibbs, all right, Gibbs is defined as H minus TS, which we also once again recognize is work. That's what this is, okay? It's the maximum work function, all right? And so now that means, I know where the constant volume, the constant volume comes from the fact that we're dealing here with U, okay? So now with Gibbs, because we're dealing with H, we need constant pressure, okay? So that comes from now TdS greater than equal to dH. And because now we're talking about dH, constant P and du is constant V. Okay? And so now similarly what this gives us is dG at also constant T, if I drop off that T right there, but now at constant P, this has to be negative for all spontaneous processes. And hopefully you remembered that from your Gen Chem or even your biochem, Gibbs has to be negative for a spontaneous process. Okay? So a few more words on this. So let's see here. What about in the case of when these are equal to 0? Okay, so when dt dv equals 0, or when dg at constant p equals 0, this is a special condition in chemistry that we call equilibrium. And we will spend a whole module on the thermodynamics of equilibrium. But this gives us the thermodynamic basis of equilibrium. When these quantities are negative, that gives us a spontaneous process. And because of these relations of the first law, both of these quantities are often referred to as the work function or the maximum work function. Okay? So I do want to spend a little bit of time describing where the alternative name for these comes from, the free energy. Why is it called Gibbs free energy? And oops, so as a reminder, sorry, I forgot I had this reminder slide. Here are all of our criterion for spontaneous processes. You should know these, okay? dg, dA, dH, du, all at their constant respective natural variables must be negative for all spontaneous processes. And of course, entropy must increase, must be positive for all constant processes, okay? So now I'm gonna set up